Okay, geotrig, this is lesson 3. This is day 3, we'll say. So, let's do some definitions here. What does it mean to be a concave polynomial? Concave polynomial, guys. It's a polynomial, so it's a simple closed figure. But concave means that one or more vertex points inward. Concave. Cave. When you think of a cave, you see of an indent. Yes? So the easiest one for me to draw would be a concave pentagon. So now, not only do we have regular pentagon, we have irregular pentagon. We have a type of irregular pentagon, and that is a concave pentagon. So a convex is all vertices point outward. And so that is a convex polygon. Convex pentagon, to be more precise. Okay? So all of your vertices, all of your corners, end up pointing outwards, nothing to the middle. Now, another way that the book likes to say, hey, is this concave or convex? A little bit formal definition is if I take this convex or concave one, I'm going to make it a little bit larger so we can see it, okay? Is, by definition, for it to be concave means that if I can choose 2 points anywhere, okay, and connect them with the straight line, and I'll never leave the inside. Hey, it works, right? What happens if I connect those two, the top two? That was a bad line. But I now just left the inside confines of the polygon, so therefore it's concave. If I try to do the exact same thing with a convex one, I'll never be able to leave, right? I can always get to another point with a straight line, never leaving the inside. So that's a little bit more formal definition. Similar means to be the same. So we have similar angles. They look the same. And the thing is about similar, though, doesn't always have to be equal. It's the same. Or should I say, instead of saying it's just saying same, maybe I should put in quotation and say
likewise.
Likeness. I don't know if that's the right way to spell it. It's a likeness. When we say things are similar, kind of you and your parents are similar. You look the same, but you're not, right? So when we're talking about polygons, that's where it comes into play. I have an equilateral triangle. I have another equilateral triangle. They are similar. They're similar because we will have angles that are the same, but our sides will not be the same. If angles are similar in corresponding positions, what do I mean by that? The top angles correspond to each other, the bottom left correspond in the same order, that means they are similar. And if they're similar, they will have something we call a scale factor. And the scale factor is just the ratio. It's the ratio of sides. The very important thing about the scale factor is that you have to stay the large over the small, the left over the right, or vice versa. You can't mix them up. So you can't choose to take a side from, say, the small one here and put it over this one, which corresponds, and then choose to put the large triangle over the small triangle for the other pair. So the scale factor is the ratio of corresponding sides. Maybe put corresponding sides in there if you want. We talked a little bit about this. The measures of blank angles must be equal. I used the word several times already. Corresponding angles must be equal. The lengths of corresponding sides must be what? Similar? I don't know if we can say equal because they don't always have to be equal. Look at the two triangles on the bottom. This side and this side are corresponding. They don't have to be the same length. It must be, I'm going to say that instead of must be, how about we say must have a scale factor. Whoa.
Why did you write that?
Scale factor. Or common, actually common scale factor. They have a common scale factor. So each one of those sides below, the ones I got marked in red, the ones I got marked with a circle, and the other ones with the square, okay? I'll take those off probably anyways. But those sets of corresponding sides of large to small or small to large, left to right, right to left, it doesn't matter. They're all going to have the same scale factor. So it's 1 to 2, or 2 to 1, or 3/4. Okay? It could also be 1 to 1. That's interesting too. So we move on to similar triangles. Similar triangles, they have same angles and a scale factor. So they have a scale factor between sides. We'll even say corresponding sides. And the cool thing about it is that when you have two angles in one triangle have the same measure as two angles in another triangle, the triangles are similar because the other angles must also have equal measures. We're going to use this one quite a bit. I'm going to erase the side stuff on there. What it says, guys, is that if I said this angle is equal to that angle, and I go back and I say these two angles are the same, what does it mean about angle A and D? Well, think of this. In triangles, how many angles are there?
3,
How much do they add up to?
180.
So if you know two of them, is it easy to find the third?
Yeah.
And if those two are the exact same angle measures as another two in another triangle, well then we can find that third angle too.
Yeah.
And it happens to be the only option we have is for those two angles that we just found to be the same. And so, therefore, these two angles have to be the same. And that way we're going to use this in class is 2A implies 3A. If you know two angles, it implies you know all three. Or if two angles are congruent in a triangle, that means three angles are congruent in the two triangles. So, knowing something about a scale factor and angles and what we need to do here is we need to solve for x and y. Now to solve for x and y, there's a couple things that we need to do. We need to, number one, show they are similar. Because if they're similar, therefore, I can use a scale factor, get a common ratio to solve for x and y. Are these similar? Yes or no? Who says yes? Who says no? Who's not voting?
They're similar.
You just voted, guys. Now, they are because they share an angle here. That's a name for that. What is that? No. Vertical angles. They're vertical angles, and they share one over here that has 2 tick marks on it, and so does this one. So if 2 angles are the same, that implies
They're equal.
all 3 are the same, right? Or the other pair is the same. So now we can say for sure that all 3 angles correspond with another 3 angles in the other triangle. That's awesome. Now we can start to set up our scale factor. The scale factor, guys, is the one pair of angles. You look to their sides and say, which one of these has numbers? No variables. So, what do I mean by that? Let's look at the vertical angle ones. This one opens to this side, which is 4, right? That corresponds with the angle that's opposite the same type of angle, which is y. Are those both numbers? No. So I don't want to use that. But I can say it's 4 over y, or y over 4. It matters which way you want to go. So let's look for another one. We have x down here. So if we knew this one wasn't a pair, that can't be a pair because I won't know it. But 5. 5 is opposite the red band here, right? The angle opens up to that. So let's go find his partner over here. And it opens to 7. That's number pair. So let's do left to the right, left to right, and write down these ratios, starting with the one that I know. Now you don't always have to use the one you know first, but I like to put it first. And we just said it was 5 to 7. Guys, that's going to be the same ratio as any other side on that left triangle to its corresponding right triangle side. So someone give me another left angle or left side. 4. That is equal to 4 is to y. Why is that again? Because 4 is opposite the single band tick mark, which opens itself to y. And the last one is the x, which corresponds to the double tick mark band.
Oh.
And the double tick mark band is 6. All 3 of these ratios are exactly the same. And they all will be what? Equal to
180.
5, 7.
Oh, okay.
5 to 7. So now all you have to do is solve for x and y. Guys, we can't solve 3 different fractions set equal to each other. So I suggest separating. Separate the first 2. 5 over 7 equals 4 over y. Can you solve for that? You solve by?
Yes.
Cross multiplying. 5y equals 28. Divide by 5. Y is equal to 28 over 5. I agree with that. Do not convert that to a decimal of 5 and 5.6. I mean, 5.6 is okay. Some of these won't turn out to be nice. But there's one. And And then go back and do the same thing with
7
the known ratio and the other unknown. 5 over 7 equals x over 6. 5 times 6?
30.
30 equals
7.
7x. Divide both sides by
7.
30 over 7. You down found x and y. Thing about it, guys, it didn't matter if I would have actually started with the 7 side, with the right triangle, and put it over the left. The ratios will still work and be perfectly fine. Try this one on your own, and we'll come back together. So, first of all, these similar triangles. How do we know? They're both right triangles. I need more than that. Because that would be nice, but that doesn't necessarily mean that there's a 30 and a 60 or a... Yep, they're both right. We need more than that. You're missing something. It's staring right at you. It's in the middle. Yeah, they touch, but the lines cross, forming what?
X.
Yes. And what do we know about x's? There's a certain type of angles being created right here. Vertical angles, and vertical angles are the same. You guys cannot do this problem without acknowledging the fact that those angles are the same. Now that you say, hey, I know 2 angles are the same in their triangles, that implies the others are the same too. Yes. You needed that. Now, guys, it makes your life a lot easier of figuring out which pairs are together. Now, let's forget about the whole idea of having to find the pair that has numbers. Let's just put the pairs together. Like the easiest ones. Right here. So, do we want to go left to right, right to left?
Left to right.
So we're going to go left to the right. I like to state that so that way we don't get it mixed up. I always know that I'm always putting the left one over the right one. And so that's x over z. Interesting. Okay. Equals y. Y is to the double band. The double band is to the 8, correct? And 7 is to 10 because they are opposite the 90-degree right triangle, right angle, right? Guess what? Y is pretty easy to solve for, isn't it? So let's do those quick. Y over 8 equals 7 over 10. So 10y equals 56. Or y equals 56 over 10. I heard someone already reduce it. 28 over 5. Yes? Not a problem. Guess what I'm going to do? I'm going to draw that on here. Oh, that was y. Y is 28 over 5. And if it helps, make it 5.6. Yes?
Yes.
Maybe that might help us down the road. I'm not sure. Now what do we do? You got to solve for x and z. But unfortunately, I have this wonderful term here that's a scale factor, but when I go to set it up with this one, I have 2 variables. 2 variables, 1 equation. Can you do it? No. Problem. There is a solution.
You can use a square plus b square
Yes, a squared plus b squared equals c squared, which is called the Pythagorean Theorem. Guys, we talked about that last week. Which triangle can we use that on? I actually personally would do it with the right one. Okay? Where z is the unknown, 10 and 8. Why do I use the right triangle instead of the left? Right, there's two numbers off the bat because you're given those. Can I ever make a mistake then? Because what happens if I didn't get y right? What if I accidentally wrote down 29 over 5? And then I use that number to solve for x? Going to be an issue, right? So, what's a?
8.
Okay, so 8 squared plus?
1 or 10 squared.
Ooh, what is it, guys? It's z squared because a leg and a leg. 10's the longest one. It's always opposite the 90. Equals 10 squared. 64 plus z squared equals 100.
Yeah, 100.
Z squared equals?
No, it doesn't.
You got to subtract 64 from both sides.
Oh my gosh.
40.
So, 6. Oh, that makes it a lot easier, doesn't it? Because now you can plug in 6 in for z. And then you just cross and multiply with 7/10 to get x. Our life is complete. Right? So 42 equals 10x or
42 over 10.
21 over 5 or 42 over 10. We just reduced it. So now we just found all three. Homework of lesson 3. This is day 3, page 34, 5 through 8, 16 and 24. Have a great day.